How Newton might interpret gravity was sufficient to permit us to fly from the Earth to the Moon at any point. Get yourself lost in the ticking hands of time, contemplating whether our understanding of it is simply the tip of the worldly iceberg. On its head, his discovery isn't just a hypothesis, it is a key that could unlock the doors to the mysteries of the universe, revealing a cosmos more intricate and awe-inspiring than we ever dared to imagine. How does Brian Cox's new theory challenge our conventional understanding of time, and what are the potential implications for our perception of reality? Join us on a captivating exploration through the archives of time itself as we delve into Brian Cox's recently unveiled groundbreaking theory on the nature of time in the vast universe around us. Mysteries are waiting to be uncovered, and some of these involve perplexing aspects of time and gravity, fundamental forces of our reality. Imagine a world where time behaves strangely, where it can slow down or speed up. Additionally, the force that keeps us on the ground might not be what it seems. This is the realm of Albert Einstein's theory of relativity, where our understanding of time and gravity takes an unexpected turn. Albert Einstein, a renowned name, provided us with a new way of looking at the universe through his theory of relativity. His work laid the foundation for understanding how time behaves in different situations, especially when traveling at incredibly high speeds. It all began in the early 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, revolutionized our understanding of reality. In simple terms, it tells us that the laws of physics remain the same for all observers who are not accelerating regardless of their motion. This theory introduces the concept of relativistic effects, including the famous idea that time can dilate or slow down under certain conditions. One fascinating thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving at an incredibly high speed, almost at the speed of light. Inside the spaceship, a beam of light bounces between two mirrors perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers. Therefore, the light beam must appear to travel along a longer diagonal path. The time it takes for the light to complete its journey should be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the external observer, it seems as though it takes more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the stationary observer. Understanding how things change when they move at high speeds, known as relativistic effects, is not just a theoretical concept. Scientists use massive machines called particle accelerators like the Large Hadron Collider to make particles travel at nearly the speed of light. When objects move this fast, we must consider time in a unique way to make precise predictions and calculations. Albert Einstein formulated the special theory of relativity in 1905, and it transformed our perception of the universe, particularly regarding time and motion. This theory challenges our everyday intuition. It asserts that the fundamental laws of physics are the same for everyone regardless of whether they are moving. This differs from our ordinary experience, where we assume that if something is already in motion and we add more speed, it simply moves faster. However, Einstein's theory states that there is a maximum speed limit. Nothing can travel faster than the speed of light. From this perspective, events that seem to occur simultaneously for us might not appear the same to someone moving at speeds close to the speed of light. Another concept arising from this perspective is length contraction, meaning that an object in motion appears shorter in the direction of its movement when viewed from a stationary reference point. Then there's Einstein's famous equation EmC superscript 2, which demonstrates the equivalence of energy and mass. This concept is crucial for understanding the behavior of subatomic particles traveling at high speeds and for phenomena like nuclear reactions. In the real world, special relativity is not just an abstract theory, it has practical applications. For instance, GPS technology relies on precise time measurements from satellites moving at high speeds. Due to their motion, these satellites experience time dilation, which must be accounted for in GPS calculations. Without this adjustment, navigation accuracy would be significantly affected. Special relativity teaches us that time is not uniform, it depends on motion. This idea challenges our conventional perception of reality, suggesting that our usual understanding of the universe is incomplete. According to the special theory of relativity, time is not fixed. It is influenced by motion. Some fundamental principles, such as the constancy of the speed of light and the relationship between energy and mass, have been experimentally verified numerous times. Now enter Einstein's general theory of relativity, published in 1915. This theory explores the relationship between gravity and the structure of the universe. It overturned the traditional view that gravity is merely a force pulling objects from a distance. Instead, it tells us that gravity occurs because spacetime is curved or bent. Imagine spacetime as a large, stretchy fabric. When a massive object like Earth is placed on it, it creates a dent in the fabric. If you place a smaller object like a ball near the Earth, it will roll toward the dent, similar to how objects move due to gravity. In this view, gravity is not a mysterious force, but rather the natural movement of objects in response to the curvature of spacetime. General relativity provides a robust explanation for planetary motion in our solar system. It precisely predicts the paths of planets, including Earth's elliptical orbit around the Sun. This differs from the old notion of gravity as merely a force which struggled to explain planetary movements accurately. One of the first major confirmations of general relativity came during the 1919 solar eclipse. Sir Arthur Eddington led an expedition to observe how the Sun's mass caused the light from distant stars to bend. The observations matched Einstein's predictions, validating the theory. Just as motion affects time, according to special relativity, gravity also influences time. In areas where gravity is particularly strong, time moves more slowly compared to regions with weaker gravity. For instance, if you were standing near a massive object like a black hole, your clock would tick more slowly than one set far away from the massive body. General relativity also introduced the concept of black holes, regions where gravity is so intense that nothing, not even light, can escape. The boundary surrounding a black hole is called the event horizon, beyond which escape is impossible. Einstein's general theory of relativity has profound implications for our understanding of the cosmos. Initially, Einstein added a cosmological constant to his equations, believing the universe was static. However, when it was later discovered that the universe is expanding, he called this assumption his greatest blunder. The idea of an expanding universe based on general relativity is now a cornerstone of the Big Bang theory, which explains the origins of the cosmos. Another significant prediction of general relativity is gravitational waves, ripples in spacetime caused by massive objects moving at high speeds, such as merging black holes. In 2015, scientists at LIGO, Laser Interferometer Gravitational Wave Observatory, detected gravitational waves, providing further confirmation of Einstein's theory. While general relativity remains the most successful theory of gravity, alternative ideas such as modified Newtonian dynamics, MOND, and hypotheses involving dark matter and dark energy continue to be explored. These alternatives attempt to explain anomalies in cosmic observations, though none have yet replaced Einstein's framework. Scientific progress thrives on questioning and testing established theories. While alternative gravity models exist, none have convincingly overturned general relativity, which continues to provide accurate predictions about planetary motion, light bending around massive objects, and the expansion of the universe. As we explore space travel, relativistic effects become more apparent. The twin paradox illustrates how astronauts traveling at near light speeds would age more slowly than those on Earth. This effect has real-world implications for long-duration space missions. Moreover, entropy, a measure of disorder, helps explain why time moves in only one direction. According to the second law of thermodynamics, entropy always increases over time, reinforcing the forward flow of time from past to future. From Einstein's revolutionary ideas to modern space exploration, our understanding of time and gravity continues to evolve, revealing the universe in ever more fascinating ways.